We now have a calibrated camera, and so now let's take a look at a simple method for recovering the three-dimensional structure of a scene from two images. We call this simple stereo or horizontal stereo. First, let's take a look at what calibration actually gives us. Let's say you have a calibrated camera. The question is, can we find the 3D point corresponding to its projection in the image? That is, if you have this camera right here and it's fully calibrated, and I give you a single point in the image, can you tell me where the corresponding 3D point lies? And you know the answer is no, but you do know that the corresponding 3D point must lie on an outgoing ray. And given that the camera is calibrated, we know the equation of this ray. And so here is the mapping from 3D to 2D, given a point in 3D where it ends up in the image. That's given by the internal parameters and the perspective projection equations. And the same equations can be used to figure out, given a point in the image, what the equation of the outgoing ray is. And that's shown right here. So that's all we have. So in order to reconstruct 3D, we need more information. And we do this, a simple way of doing this is by taking two images, using two cameras, or by just using one camera to take one image and then a second image after that. But here are the two images that you're capturing. They're being captured from two different locations. So imagine that you have a left camera and a right camera, and the right camera is simply identical to the left camera, but displaced along the horizontal direction by a distance b. This distance b is called the baseline, and this system with a left camera and a right camera is called a simple stereo system. And this type of vision, computer vision, is called binocular vision. It's the kind of vision that you and I use. We use two eyes to perceive depth of points in the scene. So you have your first camera and your second camera, and let's say you're looking at one point in your left camera, that's ULVL. That corresponds to an outgoing ray. We don't know where the corresponding scene point lies. But let's say somehow you were able to find the corresponding point in the right camera. That is the projection of the same scene point in the right camera. That is URVR. Now you can shoot out another outgoing ray from the right camera, and wherever those two rays intersect is where the scene point lies, the physical point lies corresponding to these two image points. So that's the idea behind simple stereo. It's the idea of triangulation. So how do we do this? So we're going to assume for the moment that we have found that the point corresponding to ULVL in the left image, the point in the right image, URVR, has been found using some method. And we'll get to that later. That's called the correspondence problem. But let's say that's given to us. If that's given to us, we essentially have four equations. We have the perspective projection equations for the left camera with all the known internal parameters. Remember, again, our cameras are calibrated. And we have the same for the right camera, with one important difference, that instead of x here, you have x minus b, where b is the baseline, which again is known to us. So fx, fy, ox, oy, and b are all known to us via calibration and the way that we have set up the stereo system right here. So given these four equations, it turns out that you can actually find x, y, and z in the scene. So you have these four equations right here, and by simply solving these four equations, you get an equation for x, for y, and for z. I highlight z here because that's called the depth of the point in the scene. And the important thing to notice here is that in the denominator for all three of these, you have UL minus UR. What is UL minus UR? It is the difference in the U coordinate of the same scene point in the two images, left and right. And that difference is what's called disparity. So you have UL minus UR, the disparity, and this disparity is inversely proportional to the depth Z of the point. That is, if a point is really close to the camera system, the two cameras that we're talking about, then the disparity is going to be large. And as it moves away, the disparity begins to shrink. And as the point goes off to infinity, the disparity is going to go to zero. What this tells you is that if you have a scene at infinity, and if you take two images of the scene, one with the left camera and one with the right camera, it doesn't really matter how far these cameras are with respect to each other, what the baseline is, you're going to get two identical images. Now, as the scene gets closer and closer, you're going to see differences in the projections, disparities, and the disparity is going to increase as the depth decreases. So that's the depth Z is inversely proportional to the disparity, and in addition, the disparity itself is proportional to the baseline of the system. This is easy to understand. If you had a very small baseline, you can imagine that the differences between the two images are going to be small. As you increase the baseline, the disparities are going to scale. That you can see right here. The disparity is proportional to the baseline. And this is an important consideration because when you're designing a stereo system, since you want to measure disparity very precisely because that's what gives you depth, you want to typically use a stereo configuration where the disparity, the baseline is large. Because larger the baseline, more precisely you can make your disparity measurements. So now here's an example of such a simple stereo system. This is from Fuji. There are many other examples. In fact, these days on mobile phones, stereo cameras are often used with shorter baseline, very compact systems, but still used to compute the depth of the scene. And then that information is then used for various types of photographic effects. All right, so now there's one little piece of the puzzle missing here, which is we said for a point UL, VL in the left image, let's assume we know where it lands in the right image. We know the correspondence between points in the left and right image. Well, we need to find that correspondence somehow. So that's called stereo matching. Once we find correspondence, then that leads to disparity. So here's an example of a left image and a right image. And the kind of disparity map we're looking for would look something like this. This is ground truth. This has been measured. This is a three-dimensional scene that was measured using an active illumination method. And then we can predict what the disparities should be once we have computed them. So this is used as ground truth to evaluate the results that we are going to get. And here, the closer the point is, the greater the disparity, and the brighter it is in the disparity map right here. Now, the interesting thing about this horizontal stereo system or the simple stereo system is that there is no disparity in the V direction, in the vertical direction. Because we know that VL is equal to VR is equal to FY Y divided by Z plus OY for both the cameras. And so they're equal. That means that corresponding points must lie on the same horizontal line in both the images. So you take image 1 and image 2. If you pick a point here, its corresponding point must lie on the same horizontal line in the other image. Okay, so now we can develop a method for finding these correspondences. This is called stereo matching once again. So let's say you take a little window in the image, your left image, and we can essentially apply template matching. But when we apply template matching, we don't need to look for the corresponding point in the entire image. We know that we have scanline correspondence. We know that the corresponding point to this point in the right image must lie on the same horizontal scan line. And so therefore we take this little template, this little window, and use it as a template to match it with all windows along the same scan line. And the point where it matches best is declared to be the match, and that is the correspondence that we use to estimate disparity. So we can compute disparity by using UL and UR here, the locations, that gives you disparity. From disparity, we can compute depth, Z, and the other two coordinates, X and Y, as well, as we have seen before. Okay, so in terms of finding these matches and doing template matching, just for the sake of completeness, I'll mention once again that there's many different metrics we can use, similarity metrics. When we do these matches, you can use the sum of absolute differences between the two windows, or you could use the sum of squared differences, which we've discussed before, or you could use normalized correlation as well. In normalized correlation, you'd want to maximize it. You'd want to find the pair that maximizes it. And normalized correlation has the benefit that if for some reason the two images have radiometric differences in terms of gain or lighting, those will prove to be less of an issue if you're using normalized cross-correlation. Okay, couple of issues with respect to stereo matching, really important issues. First, we expect the surface to have texture. If you have a textureless surface, you have nothing to really match. In other words, in this case, you have a sheet of paper. When you're looking at these folds here, these creases, well, that could be a feature that you can match in the left and right image. But when you're looking at any window, small window within this more or less flat region, there's nothing to really match there. Or another way to look at it is that you're going to get many matches between the left image and the right image. So that's not good. You need texture in order to perform stereo matching. And this texture itself should not be repetitive. So here you have a repetitive pattern. And what that does is that if you take a little window here, that little window is identical to many other windows in the same scene. And therefore, when you take a little patch in your left image, you're going to get multiple matches in the right image where they're all going to be perfectly good matches. So you're better off with surfaces that have texture, where the texture is non-repetitive. And finally, you have the issue of foreshortening. And this is just an inherent problem in stereo. In order to establish correspondence, you're going to use some window size. You can't really take the intensity at 1 pixel and match it to the intensity of a pixel in the other image. There's just not enough information that's unique there to match, so you're going to take a window. Once you take a window, that implies that you're looking at a certain area in the scene. Well, the projected area, let's say that this is a surface that you're looking at, and this is the area that we're looking at right here. The projected area onto the left image is going to be different from the projected area in the right image. And so therefore, you're not really matching the same brightness patterns. You're matching warped or distorted versions of each other. So often in stereo matching, one might try to incorporate warping techniques as well to make the matching process more robust. Now let's take a look at a few results for the scene that we just saw, which is this scene right here. And one of the key questions is when you do this matching, irrespective of what similarity metric you're using, how large should the window be? If the window is really small, you're going to get good localization, but high sensitivity noise. It's not that different from edge detection. The smaller and smaller the window, the less descriptive the pattern is, and so noise can actually throw off the matching quite a bit. So you see that this is a noisy disparity map. On the other hand, if you use a large window, you're going to get more robust matches in terms of the depth values, but the disparity map is going to be more blurred, so to speak, especially at boundaries. In other words, you get poor localization. Again, this is similar to the kind of effect you get when you use large edge detectors. You're not able to localize the edges quite as well. So one of the ideas is to use multiple window sizes. This is called the adaptive window method, where many different window sizes are used for matching, and then you choose the match that corresponds to the window size that gives you the best match. Now you have to be careful here in that when you declare the best match, you have to somehow normalize that metric using the number of pixels within the window. So here are some results. Here's a left image and the right image, the same as we saw earlier. This is the ground truth. This is what we would love to get using stereo. And if you use sum of squared difference with a window size of 21, you get something like this, which is okay for some applications, perhaps, navigation, robotics, but not for factory automation types of applications. If you use the adaptive window technique, you get a better depth map. Still a little bit noisy around the edges, but certainly more details here, as you can see with respect to this camera in the background. And stereo matching has come a long way. There are more sophisticated techniques, and here is something that's more state-of-the-art. You get a disparity map that gets pretty close to the ground truth.